So in this section, we will have some power series and try to get a function representation for that power series. And of course, in here, the functions that we are only going to use are the ones that we know. Okay? Let us recall again the definition of a power series. So we have this, the series of the form, summation C sub n, x minus a to the n starting from 0 to plus infinity, and it's expanded this way. This is called a power series centered at a. So in here, x is a variable, a is a fixed number. The cn's here, they are just constants. We call them coefficients. Okay? Some important things to note. The cn, it's the coefficient of the term x minus a to the power n. The subscript of c, that will correspond to the power of x minus a. For example, c sub 0, you have x minus a to the 0. But we defined that to be the constant, or it's equal to 1. C sub 1, it's the coefficient of x minus a. It has power 1 here. C sub 2, it's the coefficient of x minus a squared. Okay? So subscript 2, power 2 in here. And then C sub 2k minus 1. So subscript is 2k minus 1. This should be the coefficient of x minus a to the power 2k minus 1. The subscript corresponds to the power of x minus a. Okay? Now, the sum of a power series given by this is a function. Okay? This is a function such that your f of x is equal to this. Okay? So c sub 0 plus c sub 1 x minus 1 plus c sub 2 x minus 2 squared plus c sub 3 x minus a cube, etc. Okay? And the domain of this function, it's the interval of convergence of this power series. Okay? So, if we represent this as a function, we need to identify the interval of convergence of this. Okay? And the function will only have that particular domain. Okay? So this means we can represent certain types of functions as power series. Let's start with some known series. This guy here, this is known to us. Okay? 1 over 1 minus x. This is the power series x to the n starting from 0 to plus infinity. And in here, the equality, okay, the equality in here is only valid for this interval. First, why is this familiar to us? Recall, geometric series. Okay? So geometric series, it's of the form sum a r to the n from 0 to plus infinity. Or maybe you know this as sum a r to the n minus 1 and from 1 up to plus infinity. But we will use this part here. Okay? So we will use this part here. Now, this is convergent. So convergent if absolute value of R is less than 1. Okay? So in here, this A here, let's just replace it by 1. The R here, let us replace it by X. And you will get this guy here with absolute value of R less than 1, meaning absolute value of X less than 1. And if this is convergent, you can write this as A over 1 minus R. And again, we have A equals 1. That's why you have this 1 over 1 minus X. Okay? So again, this guy here, the equality is only valid for absolute value of X less than 1. Okay? Now you might ask, sir, for this function here, I can take X equals 2. And therefore, I will still have 1 over 1 minus 2. That's negative 1. This will have a this will have an answer when X equals 2. I agree. I agree that this will have an answer when X equals 2. However, when X equals 2, this guy here, it will not be the same as this. Okay? Meaning, if you have some X whose absolute value is greater than or equal to 1, this equality is not true. Okay? They are not equal if the absolute value of X is greater than or equal to 1. You will only have the equality if you have this condition. Okay? Now, remember this series here. Remember this series here with this condition, of course. Okay? We can use this in order to define other series. We can use this in order to define other series. Okay? So, we now regard the series x to the n from 0 to plus infinity as a power series representation for the function f of x equals 1 over 1 minus x with this domain. Like I said, the equality only holds when this is satisfied. So this guy here, it's the same as this guy if your x is inside this interval. Okay? If your x is outside, they are not equal. Now, like what I was saying earlier, we can use this here in order to define other power series, in order to represent functions as power series. So for example, express 1 over 1 plus x squared as a power series and indicate the interval of convergence. So this is what we know. We know summation x to the n from 0 to plus infinity. This is equal to 1 over 1 minus x if absolute value of x is less than 1. So what we're going to do is the following. So if absolute value of x squared is less than 1, or this means that absolute value of x is less than 1. Okay? If this is the case, we have 1 over 1 plus x squared. You can write this as 1 over 1 minus negative x squared. Correct? And look at this. 1 minus something. This is 1 minus something. So what we're going to do, if we use this, we will now change this x here by negative x squared. This will be equal to the sum negative x squared to the power n from 0 to plus infinity. And if we separate the x here, or the powers of x here with the constant, we will have negative 1 to the power n, x to the power 2n, and from 0 up to plus infinity. So the power series representation of this is this guy, provided you have this condition or this condition here. They're the same. Okay? So in here, provided, let me write that in another line. So 1 over 1 plus x squared, this is the power series. Negative 1 to the n, x to the power 2n, and from 0 to plus infinity, provided that the absolute value of x is less than 1. Okay? Questions?
Sir.
Next example here. Find the power series representation for 1 over 2 minus x. Solution. Again, this is what we know. 1 over 1 minus x. This is sum x to the n, and from 0 to plus infinity, provided that absolute value of x is less than 1. Now look at this. We have 1 over 2 minus x. But we want 1. Okay? Okay? We want 1. So we have to manipulate the denominator here. Okay? So that we will have some 1 minus something. We'll do it in two ways. This is one way. So first, we have 1. Let's have here solution 1. Let me put the solution in this part. Solution 1. We have 1 over 2 minus x. What we can do is to factor out 2 on the denominator. So you will have 1 over 2 times 1 minus x over 2. Okay? So this guy here is just 1/2 times 1 over 1 minus x over 2. So, if absolute value of x over 2 is less than 1, so 1 minus something here, the something is x over 2. Okay? So if your x over 2 in absolute value is less than 1, then we'll have 1 over 2 minus x. This is 1 half. 1 over 1 minus x over 2. This is equal to 1 half sum n starting from 0 to plus infinity. Then we will have x over 2 to the power n. We simplify this, we have 1 half sum n from 0 to plus infinity, x to the n over 2 to the n. And we can bring these 2 inside the summation. We will have sum x to the n over 2 to the n plus 1, n from 0 to plus infinity. So again, the equality holds for this interval. Okay? So let me just write that interval here. Absolute value of x over 2 less than 1. Okay? Thus, 1 over 2 minus x, we can write this as sum x to the n over 2 to the n plus 1, and from 0 to plus infinity in absolute, where absolute value of x is less than 2. This guy here, it's already the interval of convergence. This one is enough. Okay? And similarly, in the previous example here, this is the interval of convergence. Okay? So this is just one of the ways to write 1 over 2 minus x as a power series. Can we have another? The answer is yes. Let's have solution number 2. Solution number 2, 1 over 2 minus x. You can write this as 1 over 1 plus 1 minus x. Or this guy, you can rewrite this as 1 over 1 minus quantity x minus 1. Correct? So 1 minus something in the denominator. So if the absolute value of x minus 1, this time it's x minus 1 because this is that guy here. If the absolute value of x minus 1 is less than 1, then we have 1 over 2 minus x, which is equal to 1 over 1 minus quantity x minus 1. This is equal to the summation x minus 1 to the n. And from 1 up to plus, or from 0 up to plus infinity. Okay? That is, this time, we have a power series 2 minus x, or we have the function 1 over 2 minus x. We can represent it as a power series of this form, x minus 1 to the n, and from 1 up to plus infinity, sorry, from 0 up to plus infinity, provided that absolute value of x minus 1 is less than 1. Or here, we will have what? Negative 1 less than x minus 1 less than 1. or that we have your x must be greater than 0 but less than 2. This is the interval for this power series representation. Okay? So you see, even if I am using the same function, 1 over 2 minus x, I can write it in different, I can represent it, okay? I can represent it using different power series, depending on my mood, depending on my choice. In here, look at this. The center, it's 1. In here, the center here, it's 0. In here, the interval, absolute value of x less than 2. In here, the interval, we have absolute value of x minus 1 less than 1, or you have this interval. Okay? So basically, if you have a function, you can write it, possibly, you can write it as a power series with center A, and then you can write it as a power series with another center, say B, and another power series with another center, etc. And depending on the center, of course, your interval will also change. Okay? Next, obtain a power series representation for x cubed over x plus 3. So in here, again, let me just recall 1 over 1 minus x, this is sum, x to the n equals 0 to plus infinity, absolute value of x less than 1. Now look at this. We want to find a power series representation for this function, x cubed over x plus 3. Now, I have a numerator x cubed here. This means that if I will have a power series, I will multiply it by x cubed. My center must be equal to 0. Or the center of the power series must be the same as the center of this x cubed. So the center of the power series I will construct must be equal to 0. So let us try to do that. X cubed, you can separate it, x cubed. And then you will have your 1 over, let me write this as 3 plus x. They are the same. So that I will have a center equal to 0. What I'm going to do is to factor the 3. So this will have x cubed times 1 over 3 times 1 plus x over 3. And then I'll just put the denominator 3 together with x cubed. And then I look at 1 over 1 plus x over 3. I will rewrite that as 1 over 1 minus negative x over 3. Okay? So, if absolute value of x over 3 is less than 1, then we'll get x cubed over x plus 3. This is equal to x cubed over 3 times the power series n from 0 up to plus infinity of negative x over 3 to the power n. Then let's just bring this inside the summation. So first, let us decompose this. We have x cubed over 3, sum, and from 0 to plus infinity, we'll get negative 1 to the n. We'll have x to the n. And then the denominator will have 3 to the n. So if we bring this x cubed over 3 inside the summation, we'll end up with the sum from 0 to plus infinity of negative 1 to the n, x raised to n plus 3 divided by 3 to the n plus 1. So this is that power series. And again, we have this. Okay? That is, we have x cubed over x plus 3. This is sum, and from 0 to plus infinity, negative 1 to the n, x raised to n plus 3 over 3 to the n plus 1, provided absolute value of x is less than 3. Okay? Questions? Now, let us talk about some properties of power series. Okay? What's good thing about power series is that we can differentiate it as long as we are differentiating inside the interval of convergence. Okay? You have a power series here. Suppose it has a radius of convergence r, which is greater than 0. Of course, if r is equal to 0, then you'll just have a single point as the interval of convergence. So you need a positive radius. It could be plus infinity. Okay? So you have a power series here with radius of convergence r. If we define this to be the function f of x inside the interval of convergence, then the function f of x, which is this guy here, inside the interval of convergence, is differentiable. The derivative of your f of x, you'll just differentiate term by term. So f prime of x, this is equal to the sum n times cn times x minus a raised to n minus 1. So just power rule. And notice, of course, when you bring down your n, you originally started from 0, that's your constant. The derivative of constant, it's equal to 0. So this will disappear. You will now start with c sub 1. So your n now starts with 1. And that also makes sense because you have a coefficient n here. N equals 0, it disappears. Furthermore, the interval of convergence of this f prime of x, it's the same as the interval of convergence of the original function or original power series. In short, the derivative of the power series, it's just sum of the derivative of the terms. So you can bring the derivative inside the summation. Again, this is only valid inside the interval of convergence. Inside the interval of convergence. Also, you can differentiate this power series. You can integrate the power series. So very much similar statement here. You have the power series has radius of convergence positive. You define the function to be the power series inside the interval of convergence. Then this function here is integrable. The integral of your f of x dx, it's just the series, and then term-wise, you integrate. And this is indefinite integral, so you will have that plus c. Okay? And take note, at n equals 0, this is your c sub 0, correct? Your constant, when you integrate it, you will have some x minus a. Sorry, you will have some x. But you can write it as x minus a. And then, so for example, from here, after integrating c sub 0 dx, this is equal to c sub 0 x plus some arbitrary constant here. Or, this is equal to c sub 0 times x minus a plus some arbitrary constant there. And look at this. If you multiply c sub 0 with negative a, it's just another constant. So you can bring it to this original plus c here. Okay? But what's the point? After integrating the original constant, c sub 0 earlier, it will now have x minus a. So n equals 0, n equals 0 here, x minus a will have power 1. Okay? And just like before, it only means that you can bring this integral notation inside the power series. Again, provided you are integrating inside the radius of convergence or inside the interval of convergence. Okay? So we can use this differentiability here and integrability to define other power series or to represent the power series as some functions or vice versa. For example, find the power series representation for 1 over 1 minus x quantity squared. Okay? Solution. If we get the derivative with respect to x of 1 over 1 minus x, so this is just derivative with respect to x of 1 minus x raised to negative 1. This will just be negative 1 times 1 minus x raised to negative 2. By chain rule, multiply this by negative 1. So this is just equal to 1 over 1 minus x quantity squared. Correct? So, if absolute value of x is less than 1, then 1 over 1 minus x quantity squared. This is just the derivative with respect to x of 1 over 1 minus x. But we know 1 over 1 minus x, we have a power series representation for that. It's x to the n running from 0 to plus infinity. So this is just the sum n from 1 up to plus infinity of n x raised to n minus 1. Okay? So that is 1 over 1 minus x quantity squared. This is equal to the sum from 1 to plus infinity of n x raised to n minus 1, provided the absolute value of x is less than 1. Okay? Next. Obtain a power series representation for Ln of
Sir,
1 plus x. Yes?
can you go back? I just had one last thing to finish writing.
Okay.
Thank you, sir.
You're welcome. So obtain a power series representation for Ln of 1 plus x. Okay? So from here, we have, this is what we know, 1 over 1 minus x. This is sum x to the n from 0 to plus infinity. Absolute value of x less than 1. And then we can write 1 over 1 plus x. We can have a power series representation for this. So let me write here solution. 1 over 1 plus x, we can write that as 1 minus negative x. Sorry, 1 over 1 minus negative x. So this can be written as negative x to the power n from 0 to plus infinity, or you have sum n from 0 to plus infinity of negative 1 to the n, x to the n, provided that absolute value of x is less than 1. Okay? Now, look at this. Integral of 1 over 1 plus x dx. This is equal to ln of absolute value of 1 plus x plus the arbitrary constant c. Okay? Correct? So if absolute value of x is less than 1, then we have the following. Ln 1 plus x. Take note, in here we can now remove the absolute value in this part, because your absolute value of x is less than 1. So even if your x is negative, it's greater than negative 1. your 1 plus x will still be positive. Okay? So again, from here, you will have negative 1 less than x less than 1. So when you put your x, or when you take your x inside this interval, 1 plus x will still be positive. In fact, you can show that from here. From here, you add 1 to everything. You will have 0 less than x plus 1 less than 2. So this guy here, it's greater than 0. So 1 plus x is positive. So you can remove the absolute value. Ln is still defined. But anyway, you have ln of 1 plus x plus the arbitrary constant c. This is the integral of dx over 1 plus x. But as a power series now, this is just the integral power series from 0 to plus infinity, negative 1 to the n, x to the n, dx. Or this guy here, it's the sum, and from 0 to plus infinity, negative 1 to the n, integral x to the n dx, which is equal to sum, and from 0 to plus infinity, negative 1 to the n, x to the n plus 1 over n plus 1. Of course, you can write the plus c in here, but we already have that one here. Okay? Questions so far? Now, the last thing to do here is to identify what this arbitrary constant is. We need to identify that actual constant. Okay? In order to identify that, we will use the fact that the equality holds here. The equality holds for this case, absolute value of x less than 1. The equality holds. This is constant, whatever your x is. Okay? So now, look. What we're going to do is to let x equal 0. Before that, let us expand this. When n equals 0, you'll just have x. When n equals 1, you will have minus x squared over 2. When n equals 2, you have plus x cubed over 3, plus etc. Correct? So, if x equals 0, then you will have ln of 1 plus 0 plus c. This is equal to what? At x equals 0, this is 0, this is 0, this is 0, etc. This is equal to 0. But ln of 1, that's also equal to 0. So, or c, this is equal to 0. Therefore, ln of 1 plus x, the power series representation, it's just negative 1 to the n, x to the n plus 1 over n plus 1, and from 0 to plus infinity, provided the absolute value of x is less than 1. Okay? Questions? Okay? Next here, use the previous example to find the sum. Negative 1 to the k minus 1 over k 2 to the k. K starts from 1 up to plus infinity. Okay? So it's said we need to use the previous example. So from the previous example, we have the sum negative 1 to the n, x to the n plus 1 over n plus 1, and from 0 to plus infinity, this is equal to ln of 1 plus x. Let me write ln 1 plus x on the other side. So this series here, it's equal to ln of 1 plus x, provided that absolute value of x is less than 1. Okay? Let us adjust this. Suppose we start with n equals 1 instead. Okay? We have summation n equals 1 up to plus infinity. What will happen to the powers? We have here negative 1 to the power n. It starts with n equals 0. Therefore, in this side, negative 1 will have power n minus 1. Because if n equals 1, 1 minus 1 there, it's 0. It's the same as this. When n equals 0, you have n equals 0 here. And then, in here, when n equals 0, n plus 1 is equal to 1. Similarly to this, n plus 1 is equal to 1. Now that we are starting with n equals 1, the power of n will just, the power of x will just be n. And the denominator is also n. Follow? Okay? So how are we going to use this to find this sum here? We take x equals 1 half. 1 half, the absolute value, it's still less than 1. Which means the equality here still holds. We will have ln of 1 plus 1 half. This is equal to the sum. And from 1 up to plus infinity, negative 1 raised to n minus 1, 1 half raised to power n divided by n. But this is just sum And from 1 up to plus infinity, negative 1 to the n minus 1 times 1 over 2 to the n all over n, or this one here, it's the sum from 1 up to plus infinity, negative 1 to the n minus 1 all over n 2 to the n. And that's precisely this guy here. So let's just replace n with k or whatever. We can even retain the n. But anyway, we have here sum 1, sum from n equals 1 up to plus infinity, negative 1 raised to n minus 1 over n 2 to the n. This is ln of 1 plus 1 half, that's 3 halves. So this is the exact value of this sum. It's just ln of 3 halves. Okay?